Okay, so we're going to go ahead and continue with this next example. So directions here ask us to find the Taylor series for the function f of x equal to x cubed minus 10x squared plus 6 about x is equal to 3. Okay, so um, again, let's go ahead and start with our function f of x, which is x cubed minus 10x squared plus 6. Um, and let's go ahead and take the first couple of derivatives of this. So we see that f prime of x becomes 3x squared minus 20x. F double prime of x becomes 6x minus 20. F triple prime of x becomes 6. And every derivative after this becomes 0. So this is a brand new situation for us because um, like we haven't looked at a polynomial yet, and we know that derivatives of polynomials eventually become 0. All the other functions that we've looked at, like as we start taking more and more derivatives, we wind up getting some other non-zero function that we can evaluate. Okay, so we know if we're going to center our Taylor series about x is equal to 3, we want to evaluate the function and all the subsequent derivatives at 3. Okay, so when you simplify this, you're going to wind up getting negative 57 for f of 3. For f prime of 3, you get negative 33. For f double prime of 3, you get negative 2. For f triple prime of 3, you get 6. And then for every derivative after that, you're going to wind up getting 0. Okay, so we can go ahead and write our Taylor series for this function about x is equal to 3 as the sum from 0 to infinity of the nth derivative at 3 over n factorial times x minus 3 raised to the nth power. Okay, and we can actually express this either as a finite polynomial or as an infinite polynomial. If we think of it as an infinite polynomial, every term from the fourth derivative evaluated at 3 and beyond, the term for that series is going to wind up being 0 because the coefficient is 0. Okay, so I'm going to list the first few terms of this series. So the first term is going to be f of 3. So f of 3 is negative 57 divided by 0 factorial, which is 1, times x minus 3 to the 0 power, which is 1. Okay, plus the next term, which is negative 33 over 1 factorial times x minus 3 to the first power, plus the next term is f double prime of 3, which is negative 2 over 2 factorial times x minus 3 squared, plus the next term, which is f triple prime of 3, which is 6 over 3 factorial times x minus 3 cubed. And I'm not going to list any terms after that because all those terms are going to have coefficients of 0. Okay, so I'm just going to simplify this. We get negative 57 minus 33 times x minus 3 to the first. And then I'm going to pull the minus out front. 2 divided by 2 factorial is just 1, so that's minus the quantity x minus 3 squared. 6 divided by 3 factorial, that's 6 divided by 3 times 2, which is also 1. So the next term is going to wind up being plus x minus 3 cubed. Okay, and that right there is the Taylor series for that polynomial about x is equal to 3. Okay, so I want to see what you guys do with this one. So for the next example, directions say given f of x equal to rad x, find a third degree Taylor polynomial centered at a is equal to 1. Okay, so go ahead and pause the video while you work on that, and then you can check what you came up with what I came up with. Okay, so the way that we are going to denote a Taylor polynomial is we are going to write it as t, and then we're going to give it a subscript of whatever the degree of our polynomial is. So this is, because this is going to be a third degree Taylor polynomial centered at 1, this is going to be t sub 3 of x. Okay, so the way that we would represent t sub 3 of x is it would be, again, if we're going to center our polynomial at a is equal to 1, that will be f of 1 plus f prime of 1 over 1 factorial. If we're centering it at 1, that's going to be times x minus 1 to the first power. The next term will be f double prime of 1 over 2 factorial times x minus 1 squared. The next term will be f triple prime of 1 over 3 factorial times x minus 1 cubed. Okay, so what we need to do is we need to figure out what f of 1 is going to be, f prime of 1, f double prime of 1, and f triple prime of 1. And then we can go ahead and plug into that Taylor polynomial formula. Okay, so f of x is rad x. We know that f of 1 is going to be equal to 1. F prime of x is going to be 1/2 x to the negative 1/2 power. When we evaluate that at 1, we get 1/2. F double prime of x will be negative 1/4 x to the negative 3/2 power. And then when we evaluate f double prime at 1, we get negative 1/4. F triple prime of x is positive 3/8 x raised to the negative 5/2 power. When we evaluate that at 1, we get 3/8. Okay, so we're just going to plug that into our formula here. So t sub 3 of x, our third degree Taylor polynomial, is going to be equal to f of 1, which is 1, plus f prime of 1 is 1/2 over 1 factorial times x minus 1 to the first, plus the next term is f double prime of 1, which is negative 1/4 over 2 factorial times x minus 1 squared. And then our next term is f triple prime of 1, which is 3/8 over 3 factorial times x minus 1 cubed. Okay, and then we're just going to go through and simplify term by term. So we get 1 plus 1/2 times x minus 1 minus 1/4 divided by 2 factorial, that's 1/8 times x minus 1 squared, plus 3/8 divided by 3 factorial, that's going to wind up simplifying to 1 over 16 times x minus 1 cubed. Okay, and that right there is your third degree Taylor polynomial centered at a is equal to 1. Okay, so next example asks us to find a 7th degree Taylor polynomial for f of x equal to the cosine of x centered at a is equal to 0. All right, so we did this on the prior video. We know that the Mach series for cosine is going to be, hopefully we have this memorized, the sum from 0 to infinity of negative 1 to the n power times x to the 2n power over 2n quantity factorial. Okay, so if we want to like expand out the first few terms of this, when n is equal to 0, we get 1. When n is equal to 1, we get minus x squared over 2 factorial. The next term would be plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus, and so on and so forth. So if we want to write the 7th degree Taylor polynomial, that is t sub 7 of x, we just want to list the terms of the polynomial out to the 7th degree term, which we have an issue with here because there is no 7th degree term. But there actually is a 7th degree term, but it just so happens when we eliminated the terms in the Maclaurin series for cosine, we eliminated the terms that had 0 as a coefficient. And all the terms of odd degree had 0 as a coefficient. So actually in this particular case, the 7th degree Taylor polynomial happens to be a 6th degree polynomial. So it's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And again, it's technically not a 7th degree polynomial, but it is because the 7th degree term just so happens to be 0 x to the 7th divided by 7 factorial, which is 0. Okay, we're just not going to list that 7th degree term. Okay, last example. I want to see you guys give this example a try. Okay, so you're asked to evaluate the limit as x approaches 0 of e to the x power minus 1 minus x all over x squared. Okay, so go ahead and pause the video to do that, and then we'll go ahead and work that one out. Okay, so I would have expected you guys to work out this limit like so. If we try using direct substitution with this, the way that it's written right now, we would get e to the 0 power, which is 1, minus 1, minus 0, which makes the numerator 0, over 0. The denominator is 0, so this is a candidate for L'Hopital's rule, which would give us the limit as x approaches 0 of e to the x power. The derivative of 1 is 0, minus the derivative of x, which is 1, all over our derivative of our denominator, which is 2x. And if we try using direct substitution again, we get e to the 0 power, which is 1, minus 1. The numerator is 0. The denominator will be 0 as well. So that's 0 over 0, which means we can use L'Hopital's rule a second time, which would give us the limit as x approaches 0 of the derivative of the top is e to the x power. The derivative of the bottom is 2. And now we can use direct substitution. When we plug 0 in for x, we get e to the 0 power, which is 1, divided by 2. The value of that limit is 1/2. Let's work through this limit in a completely different way. Okay, so let's do this using, because we're taking the limit as x approaches 0, let's go ahead and use the Maclaurin series to represent let's use the Maclaurin series for e raised to the x power to represent the function e raised to the x power. Because we're taking the limit as x approaches 0, we're going to go ahead and take the Maclaurin series or the Taylor series centered at 0 for e raised to the x power. So using the Mac series for e raised to the x power, we can rewrite this as the limit as x approaches 0. So again, the Mac series for e raised to the x power is the sum from 0 to infinity of x to the n power over n factorial. Okay, so let's go ahead and list out like the first several terms of that summation. Okay, so first term when n is equal to 0 is going to be 1, plus next term is x to the first over 1 factorial, which is x. Next term is x squared over 2 factorial. Next term is x cubed over 3 factorial plus x to the fourth over 4 factorial plus so on and so forth. Minus 1 minus x all over x squared. Well, when we do the Maclaurin series expansion, we can go ahead and cancel 1 and negative 1 and x and negative x. So doing so is going to give us the limit as x approaches 0 of x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus, it's going to continue on forever, all over x squared. And then we're going to take each term in the numerator and divide by x squared. So when we do so, we get the limit as x approaches 0 of 1 over 2 factorial plus x over 3 factorial plus x squared over 4 factorial plus, and so on and so forth. And as x approaches 0, all of these terms after the first term, when you plug 0 in the place of x, those are going to wind up going to 0. So this is just equal to 1 over 2 factorial, which is 1/2. So it gives us an entirely different way, yet a mathematically valid way to work through evaluating the limit for that function. All right, so that's going to go ahead and wrap up this video here.